everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we start the last major topic of the Algebraic Calculus 1 course, which is in the direction of the logarithm and exponential functions and an analysis of our third important conic. The star of the show today is the curve given by equation xy equals 1. This is the standard hyperbola. And it's closely related to and sort of generates the exponential and log functions. Although these are in quotes because the usual approach to these functions is not adequate from our point of view. It involves performing infinite numbers of operations, which we are not allowed to do. So we have to reconfigure this so that we're able to say everything in a purely algebraic and finite and computable way. Okay, so here is the function or the curve xy equals 1. There is one branch and there's another branch symmetrically on the other side of the origin. Okay, for example, the area, say formed by a segment, say we go from 1, 1 to 2.5. Now for us, the crucial quantity is the signed area, which is really the area of the region emanating from the origin to the curve with these straight lines. So that would be the area in red. In classical calculus, one looks rather at areas under curves, what we call the signed x area, or perhaps signed y area. Now, exactly for this curve, these two ways of looking at things are effectively the same. Because of the defining property of this hyperbola, it means that if we take a point like this and we go straight down to the x-axis, as parallel to the y-axis, and then we look at this triangle here, well, this triangle, it's 1, 0 this way and 1, 1 that way, so its signed area will be a half. And if we look at the signed area of the corresponding triangle formed by this point, so we go over 2 and up a half, its signed area will also be 1/2. So all of these triangles formed by points on this curve and their projections down onto the x-axis, or in fact also to the y-axis, all have the same areas. And that's the reason why the red signed area, whatever that might be, is going to be equal to this green signed area, whatever that might be. So the way to see that is start with the red region, okay, and then add this triangle here. So we're adding a half. We get this bigger region. And now subtract this triangle, which also has signed area 1/2. So exactly cancels out what we just added. And we're left with the green area. So we go from the red area to the green area just by adding and subtracting two triangles with the same signed areas. That's why they're the same. So that's a very important point. And it turns out that in this case, when we go from 1 to 2, both of these regions are what's often called log 2. Sometimes ln 2, but we're going to try to avoid that. We'll stick with log 2. But the actual definition of this is more problematic because these signed areas don't exist exactly for us. They only exist as approx areas. Okay, so there are going to be three important planar geometries floating around here. The blue one, which is basically our standard Euclidean geometry. The red one, which is our relativistic geometry. And this new one, the green one, which is also a relativistic geometry, but a little bit different from the red one. In any case, I do want us to think about these three things sort of at the same time so that the theory of circular functions, or cosines and sines and tans and so on, the theory of relativistic hyperbolic functions like cosh and sinh and so on, and the theory of the exponential and the log. These are all part of the same landscape, okay? And the techniques that we use to study one of those groups will apply more or less in some form to the others as well, right? So that's a very important idea that we're studying the whole thing really at the same time here once we have these three geometries under our belt. Okay, so to describe these uniformly, we're going to make a slight shift to a vector space point of view. So we're going to look at the two-dimensional vector space of vectors as opposed to the affine plane of points, because we want a linear structure here. We want to be able to add vectors and to scale or multiply them and have that familiar linear structure. Okay, so that's our starting point, and then we're going to impose geometry on them. And these three geometries, the blue, red, and green, are sort of associated with these algebraic structures. And one way of thinking about how they arise is by thinking about identifying these vectors, these little row vectors, with matrices, 2 by 2 matrices. So I recall that this is really how we get complex number arithmetic, by identifying the point AB, or the vector AB, with the matrix AB minus BA. The thing here is that these matrices can not just be added, but they can also be multiplied. And that's how you get the usual blue complex numbers. With the red complex numbers, it's very similar, except that now we identify our little vector AB with a 2 by 2 matrix ABBA. Okay, and now the transition to the green story. We're doing something similar. We're going to identify our vector AB with the 2 by 2 matrix A00B. Just a diagonal matrix with A and B along the diagonal. Yes, that looks simpler than these, and that's typically what happens. The green story is usually simpler looking. Now, another way of thinking about what we're doing here is we're working in the world of 2 by 2 matrices, and there's a really nice basis for that space, which is maybe not the standard basis you learn in linear algebra, but it's this one here. So starting with the identity matrix 1, 0, 0, 1, which we're going to sort of use the symbol 1 for. I might write the 1 like this, so it's definitely something different from the usual one. It represents this identity matrix. And then there's this matrix I, 0, 1, minus 1, 0. Then any such matrix is just a linear combination of the 1 and the I, giving us our usual complex numbers. We can also introduce J, 0, 1, 1, 0. Then a matrix like this is a linear combination of 1 and J, and we get the red complex numbers. Correspondingly here, what we have to introduce is a fourth matrix, which is the fourth one sort of to complete the story, so we have a nice basis. This is K, which is 1, 0, 0, minus 1. Then indeed, these two span the diagonal matrices. Any diagonal matrix can be written as a linear combination of 1 and K. And so we get a systematic kind of threefold symmetry in these complex numbers. We have blue complex numbers involving I's, red complex numbers involving J's, and green complex numbers now involving K's. So this forms us an algebraic setting in which we can discuss the corresponding geometries. Okay, so now let's look at this green geometry and the associated complex numbers. So we have our vector space consisting of vectors like A, B, and we're going to give this vector space a new algebra structure using the identification of this vector with this diagonal matrix. So the vector AB is going to be identified with the matrix A00B. And what that amounts to at the level of multiplication is very simple. The vector AB times the vector CD will just be AC, BD. This is the simplest possible algebra you could think of on vectors. So if you asked a 10-year-old, how do you do algebra with vectors, do you think? You add them component-wise, you subtract them component-wise, and you multiply them component-wise. That's the simplest possible thing. That's exactly what we're doing here. We're also going to introduce special objects or vectors. The vector 1, which is 1, 1, which corresponds to the identity matrix, and this vector k, 1, minus 1, which corresponds to the matrix 1, 0, 0, minus 1 that we've already talked about. So now we can take a vector, say z, which is AB, and we can express it as a linear combination of these two. A little bit of thought shows that the coefficients have to be a plus b over 2 and a minus b over 2. So AB is equal to a plus b over 2 times 1 plus a minus b over 2 times k. So this is then a combination of 1 and k, and let's write it as alpha plus beta k. So the alpha and beta here are sort of parallel to a and b, but they are not the same. They are not the same. Alpha is explicitly a plus b over 2, and beta equals a minus b over 2. And we might call alpha the real part of this complex number, green complex number, but we're just working in the green setting now. And beta, we'll call that the imaginary part of the complex number z. The other thing that's important in complex number theory when you're just starting is the complex conjugate. And, well, we're going to define the complex conjugate of z bar, so expressed with a bar on top, to be the vector BA. Now, that might not look like a complex conjugate, but when you consider it in the notation with the 1 and k, it turns out to just be alpha minus beta k. And now let's introduce the notion of quadrants of a vector. So if z equals AB, then the quadrants of z is by definition z times z bar. So that's familiar. And so if you multiply AB by its bar, which is BA, you're going to get the vector AB comma AB. But that's just AB times 1. And we'll forget about the 1, and so that's just a number AB. Now there's a very important theorem. This is the central theorem in complex numbers, sort of when you're setting things up, that the quadrants of the product z times w is the quadrants of z times the quadrants of w. And it's very, very easy to prove here. You don't need any fancy identity going back to Fibonacci. It's just a one-line computation because the product here, if w is say CD, then the product here is just ACBD. And the product of AC with BD is the same as the product of AB with the product CD. So it's immediate. And also we can get at this formula by recognizing that this quadrant is just the determinant of the associated 2 by 2 matrix. That's the same that happened in the blue and in the red geometries. So this is just a manifestation of the determinant property of when you multiply two matrices, the determinant is the product of the individual matrices. One more thing, let's also note that, say we have z, which is AB, and also alternatively can be written as alpha plus beta k. Then the A and B can, of course, also be expressed with alpha and betas. So A is alpha plus beta, and B equals alpha minus beta. So you might like to check that. So that then the quadrants of z, what we're defining up here, is A times B, but in terms of alpha and beta, it becomes the product of these two expressions, which is alpha squared minus beta squared. And so here you see how the green and the red geometries are two sides of the same coin in some sense. Because when we look at things this way, we're seeing the green quadrants, but when we look at the same thing in terms of alpha and beta coordinates, then we're seeing a red quadrants. Okay, so we can go back and forth in these two stories just by going from AB coordinates to alpha beta coordinates. That's a useful thing. That's something that the physicists who are working in special relativity exploit all the time, in fact. So we have these three different forms of complex numbers. These are two-dimensional algebras. They also have a geometrical aspect because we've introduced quadrants. To bring that geometrical side to the fore, it's useful to talk about a bilinear form which is closely connected to the quadratic form of the quadrants. So in linear algebra, whenever you have a quadratic form, Typically there's a bilinear form associated to it, and it's useful to see both of them. So bilinear form is like a dot product, and that's what we're talking about here. So I just want to bring that out because often when you're studying complex numbers, that side of things is a little bit obscured, not really brought to the fore. But there really is a canonical dot product floating around here, which is intimately connected with the algebraic structure of whatever complex number system we're working in. All three, the same things apply. So the geometry associated to complex numbers a, b comes from a dot product. That's often the most fundamental building block of a metrical geometry. Now we have three geometries here, so let's talk about three different dot products. The blue one, so here's the dot, and there's a little subscript b standing for blue. Okay, so AB dot CD in the blue setting. Here is the definition. It's the real part of the product AB times the complex conjugate of CD. Okay, what is that? So this is ordinary complex number arithmetic. So this is like A plus IB, and this is C plus ID. Okay, so if you take the complex conjugate, that's C minus ID, and then you multiply A plus IB with C minus ID, then take the real part of that. In other words, take the part that involves the 1 and not the I. Okay, you're going to get AC plus BD. You get minus BD ordinarily, but because there's a complex conjugate there, you get plus BD. And this is what you recognize as the familiar dot product in this two-dimensional space. The dot product is A times C plus B times D. It's the familiar Euclidean dot product. All right, so that's actually sitting there underneath the complex number structure because it can be defined purely in terms of the complex number structure by this formula. Now, in the red situation, AB dot red CD, well, it's exactly the same formula. Exactly the same formula. The real part of the product of the first thing times the complex conjugate of the second. And when you work that out, well, not surprisingly, there's a minus sign there instead of a plus sign. So we get AC minus BD. A times C minus B times D. That's the relativistic dot product. Okay, now in the green world, there's a green dot product. And you will not be too surprised to see that it's actually also given by exactly the same formula. It's the real part of AB times the complex conjugate of CD. Okay, so how do we calculate that? The complex conjugate of CD is DC. So this product is A times D, that's the first component, and then B times C. Now what's the real part of that? So the real part is like the alpha. Okay, how do you get the alpha? You take the first component and the second component, you add them and you divide by 2. So you get AD plus BC over 2. So same formula, but here there's a over 2. In each case, then the quadrants that we started with is z dot z. If we just have a single vector, say AB, and replace the CD with AB, then here we're going to get a squared plus b squared. Here you can get a squared minus b squared, and over here you're going to get AB plus BA over 2, which is the same as AB. So in each case, we recover the standard quadrants as z dot z. Now I just have to say a little word about this 2 here, okay? So there is a threefold symmetry in planar geometry that I've mentioned to you called chromogeometry, and it's a very beautiful thing. And it's going to be a major source of investigation in the 21st century, I guarantee that. But it's only sort of tangentially important here. These three geometries that we're talking about here are really essentially the same ones as appear in chromogeometry. But the way we're setting things up here is just a little bit different because of this factor 2. So in chromogeometry, it's useful to not have a 2 there. Okay, so one can just define the green dot product with just the expression AD plus BC. That makes that kind of side of things a little bit more symmetrical. Okay, but I mean, it's effectively the same, just a factor of 2. But I just want you to be aware that there's 2 possible approaches to the normalization of the green geometry, depending on sort of which way you're looking. Okay, why do we like dot products? Because they give us perpendicularity. In mathematics, perpendicularity between vectors is determined by a dot product being 0. So for each one of these geometries, we define an associated perpendicularity between two vectors. Z is perpendicular to W precisely when Z dot W equals 0. So there will be a blue perpendicularity, which is the familiar one. There will be a red perpendicularity, which this is the plane. These kind of vectors are red perpendicular. And there's a green perpendicularity. That's the x-axis. Then these two vectors are green perpendicular. Okay, so each of these geometries has a nice notion of perpendicularity that kind of goes with the quadrants. Okay, great. So now we come to the star of the show, which is the standard hyperbola with equation xy equals 1. And I claim that this is the most important curve in all of mathematics. This curve is the most important curve. There are thousands of curves. This is the most important. You might think it's the unit circle, and that would be a good guess, but not really correct. It turns out that the standard hyperbola is somewhat more important than the unit circle, although it's arguable, but I think as we go through the courses, it'll become clearer that this is more important. And it's related to the fact that the exponential and the log functions are really ultimately more important than the circular functions or the hyperbolic functions. That's just the way things are. Okay, and for us, the identifying feature of this particular curve is that it's the unit circle in green geometry. It's defined by being the green complex numbers whose quadrants is 1. Okay, and here it is. Rough picture. There's two branches. We've already talked about some of the points. There is the vector 1 and the vector k. Maybe I haven't mentioned them. So the vector 1 is the vector 1 comma 1. It's that one there. And the vector k is the vector 1 comma minus 1 there, down to there. And we've got triangles like this. And the signed areas of all these triangles are a half, even the ones emanating from the branch on this side. Okay, so this is very important because primarily, I guess, historically, it's associated with the functions exp and log, although we are going to have to think very clearly and carefully about what these things actually are and sort of how to frame discussion of them in a finite algebraic way. But nevertheless, it all centers around this curve. Okay, it's this curve which is the object of study. Just as the unit circle was for generating circular functions and the relativistic hyperbola is for generating the hyperbolic functions and their inverses and so on. Okay, so very important. So now we can reap the rewards of our analysis and our setting up of the green geometry by discussing the rational parameterization of our standard hyperbola xy equals 1. And the beauty of this story is that if you've understood what we did in the circle case and the relativistic hyperbola case, the connections with blue and red complex numbers there, we're doing pretty well exactly the same kind of thing here. Okay? So there's a unity here, and that unity helps us. What happens in one, we can expect to shed light on what happens with one of the other situations. Okay, so here is our hyperbola. And we want to parameterize it. Here is the point 1. Now we're actually shifting into sort of affine coordinates. So because I don't want to be making vectors all the place. With vector geometry, there are all these vectors, but it's easier just to draw points. So I'm going to have everything being the affine story now. But underlying it, there's the associated vector space with this algebraic and geometrical structure. So here is the point 1, which corresponds to the identity matrix, has a special role. And here is minus 1 down here, so minus 1, minus 1. This is the sort of key point that we're going to use. We're going to use lines through here. And we're going to parameterize those lines by choosing a point on the x-axis with coordinate t. So t along the x-axis. So that's the point t, comma 0. And so then we can create the line from -1 to t0, that line there. And we can calculate the equation of that line very easily. And we can calculate where the other point of intersection of that line is with the curve. And when we do that, this is what we get. So this is then going to be the point which is parameterized by t. It is the point 1 plus t, comma, 1 over 1 plus t. Okay. Have a good look at this. It's 1 plus t and 1 over 1 plus t. This is what we get when we follow our nose and do the same kind of thing that we did in the blue and the red geometries. Notably, we do not get t, comma, 1 over t. Okay? We get 1 plus t, comma, 1 over 1 plus t. We're going to call that g of t. Now, that point there also has another characterization. We're going to do the same thing that we did in the blue geometry. Through the origin, we can consider a line which is parallel to the line that we have here, there. Now, if you look at this, this line here, if you go up 1, you have to go over t plus 1 to get to this point here. So if we shift it up to here, if we go up 1 and then go over t plus 1, we're going to get a point also on this line here. So the point z, which is 1 plus t, comma 1, so 1 plus t over here and height at 1. That's lying on this line here. Okay? And so now what we can do is we can think about just taking that point z. There it is there. And let's square it. Squaring is very easy in this algebra because everything's just component-wise. So the square of this is 1 plus t squared and 1 squared, which is 1. That's going to be also on this line here because the y-coordinate hasn't changed, but it's going to be out further in this case. Now, what happens when we normalize this? In the blue geometry and the red geometry, we took this z squared and we normalized it by dividing by the quadrants of z. What is the quadrants of z? It's just the product of the entries, which is 1 plus t. So if we normalize this thing, it's very easy. We're going to get 1 plus t and 1 over 1 plus t. We're going to get exactly this thing here. So we can do this all in our heads. And it turns out that this point also then has another incarnation as being the reflection of this point in this line, green reflection. Okay, so it's a very similar story to what we had before. So now we have a beautiful rational parameterization of this curve. It's not a polynomial parameterization because this is not a polynomial. This is a quotient of polynomials. So a second best situation. Okay, but it's very simple in this case. And one thing that we can then observe is that if we take two such things and we multiply them, what are we going to get? So if we take g of t, which is on this curve, and we also take g of u is another parameter value, so also on this curve, it might also be over here, and take the product, what are we going to get? It's easy to calculate because the first coordinate is 1 plus t. The first coordinate of g of u will be 1 plus u. You multiply them, you're going to get 1 plus t times 1 plus u, which is 1 plus t plus u plus ut. And then to get the corresponding parameter, you have to subtract 1 from that. So you get that g of t times g of u equals g of t plus u plus tu. This is the group structure on this curve, the curve gamma, say, with standard parameterization 1 plus alpha, comma 1 over 1 plus alpha. Now back when we were studying the circle, we derived Leibniz's formula by asking questions about signed areas. That's always what we're interested in. You know, can we get at signed areas associated to curves? If not exactly, then perhaps approximately. So we are sort of shifting to an applied point of view here. We're talking about things which are not strictly defined. I want to keep that in mind. Okay? We do not have exact definitions of areas either for circles or for relativistic hyperbolas or for standard hyperbola here. Okay? None of those we have exact definitions. We only have approximate kind of applied maths framework at this point. Okay, but that's all right. That's still very useful. So we're going to assume the validity of the quotient rule for quotient polynumbers. There's our curve that we're talking about in the parameterization that we've just found. And then the area differential, d gamma is going to be 1 plus alpha times d of 1 over 1 plus alpha minus 1 over 1 plus alpha times d of 1 plus alpha. Now this is pretty easy to calculate. Derivative of 1 over something, that's minus the derivative of what's on the bottom divided by the bottom squared. And the derivative of this is just 1. So we just get 1 plus alpha times minus 1 over 1 plus alpha squared minus 1 over 1 plus alpha, which is easily seen to be minus 2 over 1 plus alpha. So that is very nice and relatively simple area differential. Arguably simpler than it was for the circle or for the relativistic hyperbola. So if we want to approximately find the signed area, say from t to u of this curve, well, our fundamental theorem would be 1/2 Faulhaber integral from t to u of d of gamma. So that means that we're going to have to deal with, there's a minus sign, and then the halves cancel with that too, and then we just have the Faulhaber integral from t to u of 1 over 1 plus alpha. Again, that's something that we do not have an exact expression for at this time. So we have to do the same kind of approximating things that we did for the circle and for the relativistic hyperbola. So if you go back to the Leibniz lecture, we're going to do the same thing that we did there. In fact, essentially use exactly the same formulas, but in simpler versions. So we can write 1 over 1 plus alpha, which is what we're trying to integrate, as 1 minus alpha plus a remainder, which is alpha squared over 1 plus alpha. Or we can go to 1 minus alpha plus alpha squared, in which case we have to add minus alpha cubed over 1 plus alpha. Adding one more term, 1 minus alpha plus alpha squared minus alpha cubed, and then plus alpha to the 4th over 1 plus alpha. And one more, 1 minus alpha plus alpha squared minus alpha cubed plus alpha to the 4th minus alpha to the 5th over 1 plus alpha. And it's pretty obvious how to keep going. So if we're in the range, say, from 0 to 1, so let's consider this curve, there's gamma, between gamma of 0 and gamma of 1. So gamma of 0 is the point 1, 1. And gamma of 1 is the point 2, comma, a half. So the signed area of that quantity is what I suggested would have been traditionally called log 2. Actually, log 2 would ordinarily be the area underneath that segment, but we've seen that that's the same as the signed area subtended at the origin in this fashion. So applying the same kind of reasoning as we did in the circular case, we could use the fact that we can kind of sandwich 1 plus alpha between something which is less than it, if alpha is in this range, between 0 and 1, so this thing here, this is 1 plus alpha. So if we subtract, this is positive because alpha is positive. So this whole thing is positive. So if we subtract it, we get something smaller. And this thing here, well, this quantity is going to be negative. So if we remove that, we're going to get something bigger than this quantity here. So we have 1 over 1 plus alpha sandwiched between 1 minus alpha plus alpha squared minus alpha cubed and 1 minus alpha plus alpha squared minus alpha cubed plus alpha to the 4th. And then, well, a plausible reasoning, which is not entirely obvious, is that then the Faulhaber integral respects these inequalities. And we could expect then that this quantity here, which we don't really know but would like to figure out, should be between these two things, which we can easily find. So we integrate this from 0 to 1, we're going to get 1 minus a half plus a third minus a quarter. We integrate this from 0 to 1, we get 1 minus a half plus a third minus a quarter plus 1/5. This is the integral here, and that's minus the signed area from 0 to 1 of gamma. We're getting a negative quantity here because of the orientation. If we go from here to here, the orientation is negative. Okay, so this gives a special case of Mercator's formula, that the log 2, which is ostensibly this value here that we're trying to approximate, is between this value, which turns out to be 7 over 12, and this value, which is 47 over 60. And clearly we could just jack this argument up by adding more terms. It's sort of clear that the formula is going to generalize to more terms. So we've got this nice sandwiching result, so we can get at log 2, whatever it is, in an approximately better and better fashion. All right, so this is a very important formula going back to Mercator in 1668. And it's a sister formula, I want you to think about as sister formula to Leibniz's formula for pi over 4. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.